this is code for solving unknown trajectory, monocular, using two-point boundary value problem loop. So let's just get started. So here we're just initializing our simulation parameters. And so one thing to notice is we have our dt, which in this case is 0.005. And we also have this n, which is going to be our prediction horizon. So the idea of the solver is that at a given time, t, we're going to know the true position of the object that we're tracking. And then we're going to predict some amount of time into the future where we think the object's going to go. And so that time that we're going to predict into the future is going to be n times dt. So that's our prediction horizon there. And so then we're going to optimize from the time t to the time t plus n times dt, and using two-point boundary value problem solver. And then we're going to interpolate in order to get that dt step. And we're just going to take that first step. But I'll go into that a little bit more later. For now, we're just going to initialize our state variables, and then we're going to start the loop. So again, we're just starting at the first time value, and we're going to predict into the future using this predict future function, and we're going to be predicting n times dt time into the future. So let's just take a look at that function really quick. That is down here. So we're just using linear extrapolation here. So we're looking at the true position at the time t, which here are our true trajectory functions. There's a couple more that you can play around with as well. So anyways, we're going to look at the true position at this time, and then we're going to look at the true velocity at time t, and we're just going to multiply that by how much time we're going into the future. And so that's going to give us our prediction for our theta and for our phi value. And then for our d theta and d phi, we're just going to assume that the velocity stays the same for our prediction. So if we come back up here, the next thing we're going to do is initialize our points for the optimizer for the BVP solver. And so what's important here is the initial and the final condition, or final times, because the BVP solver will make its own number of points and space them how it likes. It will not be evenly spaced like a lin space vector. And so this is just an input that we have to give, but again, it's going to be changed. So then we're going to initialize the start and end points and the guess function. And so this BCFCN is going to be our boundary conditions, and this guess is the guess. So here it's a wrapper because we're also including this z and z predicted input, and then here this is a guess wrapper because we're including z predicted time, and then this is our time final, t plus n times dt. So we can take a quick look at those two functions. They're down here. So the boundary conditions function is right here. This is going to set our initial conditions to be the current state variables. So that's going to be what the previous loop ended up giving us. And those are going to be our initial conditions for the next loop. So then we're also going to put as our final conditions the predicted values here. And then for our guess function, what we're doing here is this is just the equation of a line, which is at time t0 hitting the point z, so our initial conditions are again that z vector, which was calculated by the previous loop. So at time t0, we're going to be getting those values, and then at time t final here, we're going to be getting our predicted values. So yeah, that's our guess function. And then we're going to calculate the solution. That's with this built-in BVP FCN, which if we just take a quick look at, that's where our dynamics equations are input. And then finally, again, this vector that was created will be changed in the BVP solver, and that means that we're not certain that the solver actually evaluated the solution at time t plus 1 dt. And so here we're going to interpolate in order to get that solution, which is one step into the future, like one time step into the future. And we're going to disregard the rest of our prediction. So we're taking that one, we're interpolating here, and we're just going to take that one step. And that's going to leave us with these new state values, and we're just going to append those here. And then we're going to run the loop again, again using our previous evaluated values as our new initial conditions, and predicting again. And so that's how that works. If you want to change anything, you can change these plots over here, or the true trajectory functions. There's also an animation included in this code. So definitely that's great. And then again, this is only for one eye. In order to make this binocular, you can change these functions down here, and of course the sizes of all the vectors. The main challenge here is that MATLAB cannot, or at least cannot in a reasonable amount of time, evaluate even a single 2-point boundary value problem when the equations are binocular and extremely long. So I have written that code and it's not usable because it just runs forever. But yeah, the idea would be the same. So yeah, anyways, that is Monocular 2-point boundary value problem loop for unknown trajectory using model predictive control.